It's time to talk about a special category of frequencies: microwaves. Microwaves define the electromagnetic radiation that are shorter than radio frequencies, but also longer than infrared waves, with wavelengths ranging from about 1 meter to 1 millimeter. In terms of frequency, they have frequencies between 300 megahertz and 300 gigahertz. Think of it this way. This is the area of the spectrum where we start transitioning from electrons in conductors to photons in the void. But this is just an oversimplification of the ever-interesting quantum physics. In the practical terms of PCB, we can say that microwave applications start from around 1 gigahertz and end at 100 gigahertz at extreme. Higher frequencies push the scientific limits of PCB, at least with today's technology, and they require other structures to propagate, like waveguides and coaxial cables. Our communications mostly happen in this range of practical frequency. However, designing PCBs in these bands introduce very unique challenges, requiring good understanding of electrical impedance and the transmission line theory. In microwave PCBs, specialized materials are used to achieve very specific performance, as the PCB structure itself has a significant impact on the signal propagation. These materials include both the conductors and laminates. Look at this board, for example. This is a 2.4 gigahertz coupled line directional coupler. This is a device that splits the input power into two controlled components, outputting none at the fourth port. You can see that the design is simple, having only two interesting traces and connection jacks. However, look at the schematic at the bottom showing a part of it. Nothing is simple in designing such a simple device. The substrate as well is not standard FR4, and it should be considered to achieve the required performance. Microwave layouts require precise design techniques that include geometry and substrate analysis. They demand expertise in advanced electrical engineering topics and have dedicated simulation and EDA tools. Look at this other example. Again, this is nothing but a power splitter for signal in the frequency of 2 gigahertz. Think of it like a voltage divider, but in microwave frequency. Look at the careful design of each segment and joint on the board in the schematic, as well as the simulation of the insertion loss, which is a specific metric to analyze in microwave frequencies. By the way, this is not KiCad or Altium. This is Microwave Office Suite, which is a dedicated EDA software for microwave simulations and layout. Things get even more complicated when we are designing PCB-based antennas for microwaves. At this point, you have to understand the antenna theory with all of the details associated with it, like radiation patterns, gain, directivity, etc. A notorious, yet a very interesting topic in electrical engineering that people often refer to it as a black magic. Look at the left. This is a simple rectangular patch antenna. You see these often as GPS receivers. Even though it looks simple, achieving the desirable radiation pattern below can be challenging sometimes. On the right, you see an illustration of an array of these patch antennas with their radiation pattern. Look how complicated things can get. Just imagine these elements being arranged in other patterns, or being circular or triangular. This is where simulations become very important and very complicated. Imagine having to control the directivity of this radiation pattern in several directions. Finally, we see a meandered line antenna, which is something we see very often in wireless PCB modules in the lower frequencies of microwaves. Microwave PCBs are indeed the most difficult category of PCB to design. They require a lot of prerequisites and precision, as well as dedicated simulation tools.